This video looks at how to derive the weak field low speed approximation to general relativity. It uses the geodesic equation in the weak field and slow speed approximation to recover the Newtonian equations of motion and to show the connection between gravity and geometry. So in flat space, let the coordinates of path taken by some object be x mu and make them a function of time. That means we're going to have in the x direction, y direction, z direction in flat space, the three dimensions of the usual flat space. So in flat space, objects that are not subject to any force travel along straight lines. So the equation for that is the second derivative of the position coordinates with respect to time is 0, acceleration is 0, and the antiderivative of that gives you the velocity components, and they're constant. So the velocity vector can be written in this form, u superscript mu times the basis vector, z subscript mu, and that vector is constant. For free objects not subject to any force, they travel in straight lines. Just as we learnt in Newton's laws of motion. The velocity vector is tangent to its path and is parallel transported along that path. So this can be written as du dt is 0. U is a constant, so the derivative with respect to time will be 0. The velocity vector in flat space is parallel transported along its path, along the path the object takes. In curved space, free objects travel along geodesics. So let's think of this surface here, two-dimensional, forms a manifold, and here's some path along it, and a free object, not subject to any forces on it, will, in whatever space it's in, follow a geodesic. And a geodesic is the straightest possible path in that space. So a geodesic is a curve that parallel transports its own tangent vector, so that du d tau equals 0. I've chosen tau here, the proper time of the object. That's the time measured by a clock carried by the object. So an object carries its own clock and records its own time, and that is its proper time. So we can use the Minkowski metric to show this tangent vector is a constant vector. So here's the line element, and in terms of the Minkowski metric, and that gives us this line is equal to minus c squared, speed of light times d tau squared, and an increment of the proper time. Okay, well let's divide through by d tau squared. So there's the middle part here, divide through by d tau squared gives us minus c squared. Now, separate the d taus there, so we have dx mu d tau, dx nu d tau, times the Minkowski metric. Now, these are, as we saw earlier, the derivative, these are the velocity coordinates. And this whole object here is equal to minus c squared. So if we evaluate that, the magnitude of the velocity vector squared is u dot u, and in curved space, we use the metric and the velocity vectors, and when we carry out that operation, that sees us reducing or lowering one index, and summing out mu there, and it gives us the magnitude minus c squared. So that shows that this velocity vector is constant in relativity as well, in Minkowski space. Alright, now, in curved space, the basis vectors change from point to point. So basis vector here, here, and here, they change from point to point on the manifold or in the space. At each point in this space, the basis vectors lie in the tangent space. So at each point in this space, the basis vectors lie in the tangent space. You can see here, they're tangent to the coordinate curves. And the tangent vector lies in the tangent space to this manifold or space. We'll come across the tangent vector shortly because that's just the velocity vector we mentioned earlier. Just indicate here, this is a tangent plane. This is a two-dimensional surface, so it's going to have a two-dimensional tangent plane. And there's one of these tangent planes at each point. And the basis vectors are changing according to their position on this manifold or on the space. Alright, so here we go. So the curve followed by the object is given by these coordinates, parameterized in terms of the proper time tau. And we have each of the four coordinates in Minkowski space. The tangent vector u is u mu e subscript mu, is dx mu d tau times e mu. Alright, so let's parallel transport our vector. So the condition for that is du d tau is 0. So this vector is parallel transported along its path, means its magnitude, direction are unchanged. It's moved by slow increments along the path, alright, and held constant as it's done. Okay, so du d tau is d tau of, here's the whole vector, and we need the derivative of the components times the basis vectors, plus the components times the derivative of the basis vectors. So that's du mu d tau e mu plus. Now if we look over here, we've now taken the partial derivative of the basis vector with respect to the coordinates on the manifold or the space, and then the derivative of the coordinates with respect to tau, the parameter proper time. Okay, this bit here is important here, the use of the chain rule here. Alright, so the basis vectors are varying with respect to position, hence the partial derivative of the basis vector with respect to the position to the coordinates, times dx mu d tau. Alright, so, okay. Now du, the velocity vector with tau, the derivative of that, du mu d tau times the basis vector plus this again. Now this object here is the affine connection, or the Christoffel symbol of the second kind, times the basis vector. So this object here is equal to all of this bit in here. Alright, now expanding that out, we've got that. Now what we'll do here is, notice the mu and the mu here, we're going to swap them. They're dummy indices, and we're going to swap them with the alpha. They're also dummy indices. It doesn't matter what we name them, so long as we're consistent. So that alpha there and that alpha there will change to mu. And when we do that, we get this. And this mu here and that mu there change to alpha and alpha here. So there we've got this object. Now what it means is the basis vectors e subscript mu and e subscript mu can be factored out. We'll see that on the next slide. So du mu d tau, so factorise out the basis vectors. We're left with this object here. Now we can rewrite this derivative here in terms of d tau of this object here, dx mu d tau, which is what u mu is, plus all the rest of this. And that gives us the second derivative of the position components with respect to tau. So the second derivative plus that object there. Now, all of this is equal to 0 as the condition for parallel transport stated earlier, and from that we get the geodesic equation. So that's the coordinate form of the geodesic equation. And that gives us the component form, sorry, is what I should say, the component form. That's the component form, because this object here must be 0. The basis vectors are not 0, they exist at every point, so this object in here must be 0. And that is our geodesic equation in component form. Okay. In flat space, we only have this first part here. The basis vectors don't change. In curved space, the basis vectors change, and so we have to include this part here. This is due to the variation in the basis vectors. Okay, next bit. Right, the Christoffel symbol in the geodesic equation arises because of the variation of the basis vectors from point to point, so that the partial derivative of the basis vector with respect to the coordinates of the manifold or space is equal to this Christoffel symbol the second time times the basis vectors, and each expanded out. So there'll be a number of these here to equal this one change in the one basis vector. Okay, now the affine connection depends heavily upon the metric. It's the metric that encodes information about the geometry of the space or manifold that we're interested in, and the form of that Christoffel symbol the second kind, or the affine connection, is this form here in terms of the metric. In flat space, this object is 0, because each of these partial derivatives goes to 0. But in flat space, free objects travel in straight lines because they are not subject to any forces, and the geodesic equation reduces to the Newtonian case because this disappears. Now, this suggests that modifying the metric could lead to a weak field approximation to general relativity. Alright, so let's take our metric as being one acting on a flat background Minkowski metric with small variations in curvature provided by the second term, h alpha beta. So our metric g alpha beta will be the flat space metric of Minkowski space time here, eta alpha beta, plus this small term added on here, where the magnitude of this term is very, very small, much less than 1, very small. We also require the metric to be stationary with respect to time or very slowly changing. This is the case with the gravitational field of the sun. So you can imagine the sun, the gravitational field doesn't vary over time, or if it does, it's very, very slight. So it's a very small change. We can effectively take that change to be 0. So any derivative of the metric with respect to time, the x0 coordinate, will be 0 because we can take it as being stationary. And for many stars and other objects, we can do that. The inverse metric we can take as g alpha beta superscript, contravariant, as eta alpha beta minus h alpha beta with all the indices raised. Perhaps in another video I will show you how that comes about. Right, with these considerations, let's look at the affine connection again. So here we are, this object again. Now this time we're going to get rid of g and we're going to put eta and h in. Okay, so the inverse metric of the new form, and then with the g's I was substituting the covariant form, both indices lowered. Okay, first thing you'll notice that the terms in the Minkowski metric, eta, alpha, lambda here, they're all constant terms, so the derivative of those is just going to drop off and go to 0. And so next line down, these first eta terms have disappeared, they've gone to 0. And we're left with just the h terms, the derivatives of the h terms, I should say. Now, h is very small, very much less than 1 as we saw earlier, so very, very small changes. So a very small variation from a flat background metric is what we've done. So g has been replaced with a flat space metric, Minkowski flat space, and a small variational term here, very small. Okay. Now a small term times a small term is even smaller, so we can effectively ignore that because it will be very much smaller than this times each of these. So all that remains approximately is this flat space metric times the derivatives of this small variation. Alright, now let's consider the low speed aspect of this approximation. Now the velocity 4 vector for an object in Minkowski space is mu is dx mu d tau, gamma times dx mu dt, so proper time and coordinate time here, and it's this object here. So an observer seeing something go past him or her at a speed where gamma is significant will record these coordinates for the object passing by, where the coordinate time is gamma times the proper time, and proper time is the time measured that the object carrying a clock with itself measures its own time. Alright, so the differentials of those here, or dd tau is gamma times ddt. And now in a slow speed limit, we have gamma as approximately 1, and u mu is equal to the x mu d tau is approximately c dx1 dt, dx2 dt, dx3 dt. Remember that gamma is now 1 from up here in the slow speed case. The speed of light is about 300,000 kilometers per second, and the fastest human-made thing, one of the Voyager probes, I think, is about 19.5 kilometers per second. So it's well less than the 300,000 kilometers per second speed of light. So what we can say then is dx dt for slow speeds being much less than the speed of c is that these components can be effectively counted as being 0. So in the low speed case we have gamma is approximately 1, and the velocity 4 vector now becomes dx mu d tau is approximately c in the time component, and then each of the spatial coordinates is components is 0. Alright, so this means that we only need to consider the u superscript 0 term when dealing with the Christoffel symbol in the geodesic equation. So dx mu d tau, so here's our geodesic equation from earlier, but this time now the mu here, where or alpha, whatever it is, these two lower indices will replace with 0, 0, because dx1 d tau will be 0, dx1, dx2, dx3, d tau is 0. So all the spatial coordinates were 0, as we saw on the previous page. Spatial components. So only the time component remains. Okay, now from the previous slide we found that dx0 d tau was c, and so on. So we've got c times c here, which will give us c squared. Okay, let's have a look just in detail now. If we now take mu as 0 as well, up here mu is 0, so 0, 0, That gives a half eta 0, 0 times all this. Well, as we established earlier, stationarity means that derivative of the metric with respect to time we've taken to be 0. Gravitational field of the sun is not changing over time, roughly. Pretty well accurately it's not, so we'll take all that as 0. But down here now, when we look at 0, 0, but now I, that's not the time component now, this is now the spatial component here, is a half eta II, meaning both the same, because if you remember the eta Minkowski metric is a diagonal metric, so II there. Substituting in here, we get dividing the derivative with respect to time here, so these two terms will disappear. We're only left with this negative term on the end here because it's the derivative of h0, 0 with respect to the spatial components, spatial indices, spatial coordinates. So minus a half eta II dh0, 0 dxi is minus a half dh0, 0 dxi. Now another way we can write this is use the Kronecker delta. It writes a little bit more neatly because this defies the Einstein convention. We've got an II here and an I down there. And there shouldn't be more than two, one up, one down, that's it. So a better way of writing that would be here. Eta mu lambda dx lambda, use the Kronecker delta and sum out the lambdas, and we're left with mu. Alright, now dh0 dx minus a half dh0, 0 dx mu is gamma mu 0, 0. Next line down, so we have where the mu is, we're going to put I because we're only using the spatial indices now, we're not using the time component. So here we are, write out the equation. This is just a repeat from the previous page, except we removed the mu up here, we put an I instead. When we run that through, put that in here, we've got that to 0. Alright, now, so here's the geodesic equation now with the information put in for the low speed weak gravitational field and set that to 0. So when we take the right hand side over the other side of the equal sign, we get this object here, which we can rewrite as a half c squared nabla subscript I of h0, 0. Now in Newtonian mechanics, the force on an object due to a potential phi is given by Fi as d2xi dt squared. Assume unit mass here, so no m here. Assume unit mass, m equals 1 kilogram, minus is equal to minus nabla I of phi. And that implies if we compare this with this, remember that tau and t in the low speed case are equal to each other, approximately equal, so the same thing. This object here is equal to this, implies that h0, 0 is minus 2 phi on c squared. Next page up, so our metric can be written in terms of a potential energy function phi as g0, 0 is eta 0, 0 plus h0, 0 is minus 1 minus 2 phi on c squared, or minus 1 plus 2 phi on c squared. An example of a Newtonian potential function is the familiar one, so gravitational potential between mass m and mass m, big M and little m. For instance, maybe the sun, big M, planet, small m, all over r, the distance between them. So we have a familiar example potential function. Now we can express our one from the low speed weak gravitational field approximation in terms of the metric term g0, 0, which suggests that gravity and the geometry of nature are the same thing. Where gravity and geometry is the same thing. And we get phi, potential function minus a half c squared times 1 plus g0, 0, which is an interesting result. So this shows how gravity and geometry are intertwined, and this is the low speed weak gravitational field approximation. So here's our g0, 0 metric term, and as we saw on the previous page, we produced the geodesic equation for this particular case, low speed weak gravitational field, and we get the three spatial equations that we get with Newtonian mechanics. And here we go. We see how general relativity reduces down to the Newtonian case. So long as we have a weak gravitational field, which is small curvature, small, not massively curved, but a small change in curvature from flat, and also low speed case. And that is it.